Hello everyone, this is Yachen. Today we are very glad to introduce our paper AdaEnsemble Learning Adaptive Sparse Structured Ensemble Network for Cliff Rate Prediction. I guess we will start with introducing the background and our motivation, and then we will introduce the key components of our model architecture and its associated experiments. I guess as we all know, learning feature interactions are important to the model performance of online S-ranking system. And extensive efforts have been introduced to learn different types of feature interactions. But we observe that the practical performance of those designs can vary by dataset. So that's why we feel different feature interactions learning methods may have different advantages, and the interaction captured by them have non-overlapping knowledge. And that further motivates us to design new model architecture that be able to ensemble different kinds of feature and interaction learning module. And hopefully each feature and interaction learning approach can complement the non-overlapping knowledge. But as we all know, Ensemble is always expensive, right? So that's why we also want our model architecture to follow the conditional computation paradigm, which is to dynamically select feature interaction types and also dynamically select the optimal feature interaction depths so that to produce the final predictions. I guess then we will introduce our model architecture. Here is the overview of the architecture of AdaEnsemble. I guess there are two key building blocks of our model. The first one is the sparse mixture of expert layer. The other one is the depth selecting controller. For sparse mixture of expert layer, it has different kind of feature interaction experts. The sparse MOE layer is responsible for selecting the feature interaction experts and then dynamically activate and ensemble them. For the depth selecting controller, it's responsible for selecting the feature interaction depths, and it also controls the model on either recursively propagate and compute the deeper feature interactions or compute final predictions when reaching the selected depths. And then we will start to introduce the architecture of sparse mixture of expert layer. So in this example, we firstly compute the input embedding, and then the input embedding will feed into the gating network. The gating network is responsible for selecting the activated expert. So in this example, the expert 2 and expert n-1 was selected, and then the sparse dispatcher will send the input embedding only to this 2 expert, so that only this 2 expert was activated, and all the other expert was not activated at all. So that is way more efficient than just activate all of them. And then after these 2 experts compute the output, the sparse dispatcher will also be responsible for combining those 2 experts to build the final output embedding of this layer. So I guess for the sparse MOE layer, there is overall 3 key components. First of all, of course, the different kind of feature interaction expert, right? And then there is a noisy gating network, which is basically a neural network for selecting the top K expert per instance. And then we also apply the annealing top K gating and also the load distribution regression we will introduce later. And then again, right, the sparse dispatcher will be responsible for dispatching the input and sparsely activate the corresponding expert. And then after the expert computes the output, it will also be responsible for combining each expert's output. So here is a list of feature interaction experts that we considered. So there's always the dense layer, right, which is the most commonly used one. And also we were also considering the convolutional layer and also the multi-head self-attention layer. Finally, we also consider the polynomial interaction layer and also the cross layer. So one thing to note is that our model architecture is very general, so that we can support different kind of feature interaction expert, but not only limited to these 5. I guess here is the architecture of the noise gating network. So again, we will utilizing the input embedding to feed into, with some noise injection, of course, to feed into a 2-layer neural network to compute the embedding to represent this instance. And then there is embedding associated with each expert. So the embedding of each instance will compute the cosine similarity with the expert embedding, so that to compute the gating value for selecting the top k expert to be used per instance. And for the annealing top k gating strategy, we want to learn our model from dense to sparse, from all expert to fewer expert. So our strategy is also very straightforward. We firstly fully train all the expert and then start to decrease the value of the k, so that incrementally our model start to learn which expert to route to. And also we were also introducing the load distribution regularization, as we know that, right? So the switch transformer were using the load balance regularization. That's because for the expert the switch transformer we're using, all of them are of same type, which is basically a feed-forward network. But for our situation, right, we are using different kind of expert. So that's why we introduced the load distribution regularization. We introduced some hyperparameter as the prior to assign the instance volume to different kind of expert, so that our model can learn the representation better. Then we will introduce the depth selecting controller. So for the depth selecting controller, it mainly has two key building blocks. The first one is the estimator layer. Basically, different interaction depths have a corresponding estimator layer. It's basically a dense layer that computes the final predictions. And then there is the depth selecting network. It's a neural network selects the feature interaction depths per instance. We design a recursive propagation mechanism so that at each layer of the depths, we will decide either compute deeper feature interactions, which is to enter the next level, or compute the final predictions, which is basically exiting. So here's the visualization of the recursive propagation. You can see that basically at each depth, we will decide whether we just directly compute the final predictions or further forward propagate the embedding to build the deeper feature interactions. So you can see if we just branching out from the shallower layer, then the deeper layer will not be activated at all, which is very efficient. Here is the loss function that we applied to train our model. So besides the log loss, we also have the load expert distribution regularization, and also the load depth distribution regularization. So we use basically two coefficients to control their magnitude. And also we will also provide the prior for the expert distribution and also the depth distribution to help the model learning faster. To train the model, we design a bi-level optimization strategy. It's trying to iteratively optimizing different parts of the parameters. The first part is the expert layer and the estimator layer. So it is responsible for computing the feature interaction representations or the final predictions. The other part is the expert gating network and also the depth selecting network, which is helping the model to define which expert will be selected and also which depth the feature interaction should be. Here is basically a recap of the overall architecture. So after the embedding, right, we will forward propagate and then let the sparse mixture of expert layer to select the optimal feature interactions expert for per instance. And also there is also the depth selecting network that will decide what is the optimal depth that we should forward propagate to. And then at the selected depth, we will just branching out to compute the final prediction without further forward propagating, which will be a waste of the computing resource when we actually serving the model. And then we will start to introduce our experiments. So we firstly compare our proposed model AdaEnsemble with different kind of CTR prediction models. And we can observe that in all three datasets, our model achieved relatively better performance. And then we further compare the so-called sparse mixture of expert layer with the dense mixture of expert layer and the ensemble, and also the so-called expert-only models. We can observe that when the value of the k reaching to a certain level, then we already reach to the optimal performance, which can be compared with the dense MOE layer. But while we are achieving the nearly best optimal performance, our model's flops is way more smaller than the dense MOE layer, which means that our model can achieve the relatively optimal performance while achieving more serving efficiency. Here is a diagram we plot for illustrating the dependency of each sparse MOE layer. We can observe that our model is trying to formulating deeper feature interactions across different layers, and also there is a large number of different kind of feature interactions that we are formulating. And then here is the conclusion. It's more like key takeaways rather than the conclusion. So firstly, we propose the AdaEnsemble, which utilizing the sparse MOE layer and also the depth selecting controller that increase the model capacity without raising online inference cost. And another one is that with the conditional computation mechanism applied, the model selects the feature interaction expert and optimal depth for each example simultaneously. So I guess that's the main key takeaways that we want to give. And that's all. Thank you.